Every time it rains, mountains are cut down a little. Pieces of rock, sand, and mud are loosened and carried downhill. Streams pick up the rock debris and carry it to large rivers, which carry it on toward the oceans. If we can find out how much rock debris the rivers carry, we will be able to find out how fast the mountains are being cut down. This is the Colorado River in Utah. At this government gauging station, engineers regularly measure the river's activity. With this container, a sample of the muddy water is taken from the river. With this device, the speed of the moving water is measured. Water samples and velocity measurements are taken every 50 feet across the width of the river. Then the samples and the records are sent to central laboratories for analysis. The mud in each sample is allowed to settle out for several days. Then the water is siphoned off. The material remaining in the bottle is washed into a dish. The dishes are placed in ovens for 24 hours. This is the decomposed rock, the sediment that was in 1 pint of Colorado River water. Now each dish is carefully weighed. From the weight of the sediment in these samples, and from the depth and velocity measurements of the river, it was calculated that more than 1,200 tons of sediment were carried past this gauging station on the day these pictures were taken. By making such calculations for all the major rivers in the United States, we learn that they carry about 400 million tons of sediment into the oceans each year. At this rate, how long would it take to wash all of the land in the United States into the seas? This engineer is measuring the height and shape of the land. Such measurements have been made all across the United States. From these measurements, the total mass of the land above sea level has been estimated to be about 18 million billion tons. Divide this amount by the loss each year of 400 million tons of decomposed rock, and you'll find that at this rate, it would take about 45 million years to wash all of the United States out to sea. Has there been enough time for this to happen? Is the Earth's crust that old or older? This machine counts atoms in tiny samples of rock. Using machines like this, the age of the Earth's crust has been determined. That age is at least 4,500 million years. So, if rivers have always carried enough rock debris to level the United States in approximately 45 million years, and the Earth's crust is at least 100 times that old, and even if our figures are only approximately correct, there has still been enough time for the United States to be washed away into the oceans many times. Why then do we have any mountains left? Perhaps we can find an answer to this question if we can find out how mountains are made. One way to make a mountain is to make a pile of something. In nature, how are new materials piled on the surface of the earth? What about meteorites? Can they make mountains? Meteorites are bits of stuff from space that have landed on the Earth, but they're rare enough to be displayed in museums. It's not likely that enough meteorites have fallen on Earth to make a mountainous pile. In fact, when large meteorites strike the Earth, they're more likely to make a hole and scatter debris over a wide area. So meteorites don't make mountains. Here's another way to pile up material. This volcano, Paricutin in Mexico, started erupting in 1943 in a farmer's field. In less than a year, it piled up enough material to make a mountain over 1,000 feet high. Mount Shasta in California is over 14,000 feet high. Craters, steam issuing from cracks in the rock nearby, and hardened lava flows are all evidence that mountains like this are old, inactive volcanoes. Of all the mountains in this part of North America, these are volcanic. But what about the other mountains? What about these in Nevada, for instance? There are no craters here, no flows of hardened lava. These mountains are not old volcanoes. How then were these mountains made? These are the fossil remains of marine animals. We know that such marine animals are found alive only on the ocean floor. The fact that we find these fossils at a place 4,000 feet above sea level proves that either the ocean was once this high or that some force has pushed an ancient seafloor up at least 4,000 feet. Was the ocean once this high? Or can mountains be made by pushing material up from below? To answer this question, we'll have to gather some evidence. This is high tide at a California beach. At low tide, an almost flat rock surface is exposed. If we speed up the wave action, you can see how this rock has been worn flat by the breaking surf. Along this coast, there are a number of what appear to be flat steps, one above the other. These are called marine terraces. Each of these terraces was originally cut flat by the action of the breaking surf. The fact that these marine terraces are high above the sea proves that the relative levels of land and sea have changed. A lowering of the sea level would have affected shores in all parts of the world, and we would find marine terraces at this height along all coasts. But we don't. So these terraces prove that the land here has been pushed up. Good evidence that mountains can be made by being pushed up from below. This mountain is in central Nevada. During an earthquake on December 16, 1954, this low cliff suddenly appeared. The land moved like this. Such a break in the land surface indicates a fault or break that extends down into the Earth's crust. In this case, an earth movement along the fault made the mountain higher than its surroundings by about 15 feet. Another good piece of evidence proving that mountains can rise. This stream is carrying mud and sand, bits of decomposed rock we call sediment. When the stream reaches this reservoir, the sediment is carried into the calm water. If the reservoir is emptied, we will be able to see what happened to the sediment. The sediment has settled out in horizontal sedimentary layers. What happens to the millions of tons of sediment that are washed into the oceans every year? Will the answer to this question tell us anything about how mountains are made? This muddy water represents the sediment-laden water carried by a river. We're going to use this tank to demonstrate what happens when sediment-laden water enters a large body of relatively calm water, like an ocean. The bottom of this tank does not represent the ocean floor. On this scale, the floor of the ocean would look more like this. But for this demonstration, we have exaggerated the unevenness of the bottom to emphasize an important fact. The tiny grains of sediment settle out in the calm water. If we speed up the process with a time-lapse camera, we can show in a few seconds what in nature would happen over thousands of years. This is a new inflow of sediment. Each succeeding inflow puts down another layer of sediment. No matter how rough and uneven the bottom is, the sediment settles out in nearly horizontal layers. Over a long time, layers of sediment deeply buried under more layers become compressed and cemented into hard rock. These layers of rock in the Grand Canyon were formed from sediments deposited in water. Wherever layers of sedimentary rock are not horizontal, we know they have been moved. These layers of rock are not only tilted, they're crumpled as well. The fact that crumpled layers of sedimentary rock are found high up on mountain peaks is further proof that the Earth's crust has not only moved, but has been pushed up to form mountains. These mountains are made of sedimentary rock. And we have seen that these mountains are made of volcanic rock. There are still some mountains unaccounted for. They must be made of something other than volcanic or sedimentary rock. This rock in California is not in layers. It's not sedimentary rock. It's not volcanic either. This is plutonic rock. It's made up of crystals that have grown together. Where could such a rock have come from? It's possible to grind up a piece of plutonic rock into a powder, then reform the powder into something that resembles the original rock. The powdered rock is put into a capsule. A little water is added. The capsule is sealed. The capsule is then placed into a special oven in which very high pressure can be developed and which can be heated to extremely high temperatures. The powder is cooked at a temperature of 800 degrees centigrade and under a pressure of 48 tons per square inch. These conditions are similar to those existing several miles under the Earth's surface. Then the sample is cooled very slowly under the same high pressure. This artificial rock resembles the rock we started with, but not exactly. We let this sample cool for only 1 day. If we could have extended that cooling time for hundreds or even thousands of years, the resemblance to plutonic rock would be much closer. Lots of time, high temperature, and high pressure are needed to form plutonic rock. On Earth, the only place where such enormous volumes of rock can cool slowly under high pressure is deep below the Earth's surface. So the presence of plutonic rock in mountains is very good evidence that such mountains have been pushed up from below. This is a benchmark. It was placed here more than 40 years ago by the United States Coast and Geodetic Survey. The elevation of this benchmark has been measured 4 different times in the last 40 years. Each time it's measured, the marker is found to be a little higher than it was before. In 40 years, this benchmark and the culvert and rock beneath it have been pushed up 7 1/3 inches. That's at a rate of over 1.5 feet in 100 years. Many similar benchmarks have been placed along this railroad less than a mile apart for many miles, and each of them has been going up. This benchmark, for example, is rising at the rate of 14 inches each 100 years. And this one is going up at the rate of 6 inches per 100 years. These triangles show the locations of the benchmarks that have been rising. The average rate of uplift for this group is 19.2 inches per 100 years. If these benchmarks continue to rise at this rate, how high will they be in 1,000,000 years? So, although the mountains are very slowly but constantly being washed out to sea, we still have mountains because they keep rising, faster than erosion can cut them down. Why the Earth's crust is so restless is one of the great unsolved problems of geology today.